So we have the liveliest group making theirs, okay? And we're hurrying to get, we should be hurrying to get started before the HDR guys get here. No. What's this project all about? Okay. Last summer, I'm reading the paper. Remember newspapers, which nobody reads? Reading in the paper about this project. SEA's got 19 million bucks, only needs another 8, and they can build this wonderful project which will extend the park in the lower. I shouldn't be saying that. That gets in the. I'm competing with you.
We'll cover that a little bit too.
Okay, I didn't say that. I heard about this exciting project. I thought, wouldn't that be a neat design project, but it's really much too difficult for us to do. We start organizing, we end up with this team and talking about possibilities, and I mentioned this. And I said, gee, let's do it. And this is a remarkably challenging project. I think they've done very well on it. And I think if we can get these guys to sit down, can we find a seat for Dawn and Nick? Maybe. Do you want them facing backward? These guys know a lot about the project because we worked on it. Okay? Nick, you're up. Let's go.
Okay.
Quit
Thank you very much, Dr. Euler. We're about ready to get started. Hope everybody enjoyed lunch. Appreciate everybody coming. We are Rhombo Incorporated. Our mission statement is to think outside the rhombus. That's our company slogan. And I think you'll find that this project fits that perfectly. It's not a straightforward project. It's nothing's really a right angle, nothing's rectangular. We had a lot of problems that we had to come up with innovative solutions for. So I think you'll feel that that slogan fits it perfectly. Just like to introduce the team to start. I'm Nick Savetic, I'm the team leader, structure student. The other structural engineers, we have Carol Ng, Shar Zaman, Becky Glucksman, and then Laura Safford. And then also on the team, we have 2 construction managers, Gray Nemhoff, Nate Hyde. So a little background information and history before we get started. Some of you may remember 1952 Pittsburgh. Maybe not. You can see some similar features today, downtown Pittsburgh, the rivers, a couple bridges. But one key difference is the Lower Hill District is this area right here. Back then it was fully integrated, fully connected to the rest of the city of Pittsburgh. That changed with the construction of the Crosstown Boulevard, the Civic Arena in the 1960s, and there was a barrier between that, those neighborhoods, and the Hill District really became cut off from the rest of the city and became really socioeconomically depressed for many years. Here's where we are today. The Civic Arena is long gone, but a barrier still remains between these communities. We have the Crosstown Boulevard, and the Civic Arena site, just a very large parking lot right now, really. So it's a part of our project is to reconnect these neighborhoods and revitalize these neighborhoods. Here are the proposed plans for a redevelopment project in that area. On the former Civic Arena site, you can see all the green space and buildings that are proposed. And our team in particular has been commissioned by the Sports and Exhibition Authority as well as all the other involved organizations to work on the structural design and construction management plan for this westernmost portion of the project, which is an elevated bridge deck structure with a park on top of it, which is right over top of Interstate 579, and it'll be used to bridge the gap between those 2 neighborhoods. Here's a better architectural rendering showing a little bit of a sample of landscaping and the pedestrian walkways and what this structure will really be used for, and just give you a sense of the scale of it. Here's an aerial view of our site. You can see there's 2 existing bridges at the north and south end of our site, So we'll be going right up against those and sort of having one large deck in between those two structures. You can see a couple of the key sites nearby. PPG Paints Arena's right there, and the U.S. Steel building right to the west. Here's an aerial view showing the Bigelow Boulevard Bridge to the north, a couple approximate dimensions, and then the Center Avenue Bridge to the south. We have an existing parking lot to the east, which will be used as a staging area during construction, and then a small existing park to the west, which will also be part of our project. Just to give everybody an idea of what the site looks like from down below, this is on the interstate. You can see the two abutment retaining walls on either side. You can see all the clearance issues that we have to work with, also the lane restrictions, and then the different ramps and elevations for those. We all address those in our challenging design. This project also boasts many sustainable features, which is great. The key things, it reduces a lot of runoff flowing into the combined sewer system of Pittsburgh, a lot of increased green space, also promotes walking between communities, that's just for healthy communities, and then positive economic impacts for both the Lower Hill District, downtown Pittsburgh, and the surrounding areas. So the complete deliverables for our project include the full structural design of this deck park, and then a full construction management plan for the site as well. Like any structural design, we start with preliminary load determination, and then we've also completely designed girders, decks, bearings, piers, and all abutment and foundation components. On top of that, we did a drainage analysis for the site. With the construction management plan, all the typical documents are included in that you would expect, but the key ones for sure are the construction schedule alternatives and the cost estimate alternatives. We really communicated, the structural team communicated with the CM team back and forth really during this whole semester to iterate our design and make the most efficient design based on those schedules and those estimates. We also got a lot of input from our CM guys about crane selection, logistics for building this thing, and also the construction sequencing. To make the most efficient structure possible, we considered many design alternatives, especially with the materials. We considered both steel or concrete girders, 1-span, 2-span, or 3-span bridge layout. We considered simply supported or continuous girders, optimization of those girders, orientation, spacing, and the material grades of all of our components. We also looked into either hammerhead or rigid frame pier designs, and we optimized the placement of those piers. Along with our construction managers, we sort of consulted them at every step of the design process and iterated our designs to make sure that this thing is constructible and it is efficient. There are many different sequences for building this, and many of the loading from construction really dictated our design. So I'll pass it off to Becky, and she'll get into load determination now.
Thank you, Nick. So the first step in determining loads was determining the dead loads on our structure. We included conventional dead loads like the deck and the girder selfway, but we also had to determine dead loads due to the loads that would make this bridge a park. The couple of loads that I would like to highlight are the Engineer Lightweight Fill and the Geofoam. Engineer Lightweight Fill is a material that has been designed for intensive green roofs, and it's actually designed to be lightweight yet support the growth of vegetation. And expanded polystyrene, or geofoam, is a high-performance lightweight geosynthetic fill, and this will be used to create interesting landscape features such as swales without adding a lot of extra weight to our bridge. The next step was determining the live load, and for the live load we considered a couple different load cases. We have 4 load cases, and a lot of them are controlled by construction. One of our construction sequences uses a crane that is placed on the bridge to lift the beams, and that load case that uses the crane to lift the beams is actually in our first 2 load cases. The first load case is just the crane driving out onto the deck along with the dead load due to the girders and the deck. The second load case includes lifting a 30-ton load along with the dead load due to the girders and the deck. The third load case is important when constructing the landscaping on our bridge, and this includes a dump truck with all the dead loads except for the trees. And it should be noted that this is the load case that produced the maximum shear in moments on our bridge. And the fourth load case is the one that will be after the bridge is constructed. So it's the 90 PSF live load along with the total dead load. And the dead load or the live load of people, 90 PSF, can support the assembly load of people gathering for a Pens game, so it's enough. Also, this is the load that controlled our design because the live load was the controlling factor for the deflection. In our girder design, we considered a couple of alternatives. We considered alternatives for girder geometries, various spans, and also our structural material. For girder geometries, we considered different skews. As the skew increases, the length of the girder decreases. However, the number of girders increases. Due to the increased number of girders in the highly skewed or mildly skewed bridges, the parallel girder geometry was actually the most efficient and cost-effective solution. Therefore, we chose the parallel girder geometry. We also looked into one span versus two spans. I-579 is a very heavily traveled road, and we didn't want to put piers if we didn't have to. However, the cost of piers was not as significant as the difference in the cost of superstructure material costs. The table here highlights the $5 million difference in superstructure material costs. Therefore, we decided to move forward with the two-span bridge arrangement. For analyzing the girders, we used influence line analysis to determine the maximum shears and moments due to vehicular loads. The moments and shears due to distributed loads was fairly easy, but vehicular loads, the controlling shear was placed when the reaction or when the vehicle was placed closest to the reaction or support, and the controlling moment was when the center line of the span fell halfway between the center of gravity of the vehicle and the nearest wheel load, which is displayed in the picture on the right, if that's confusing to listen to. It should also be noted that we picked simply supported spans, and this was due to the fact that even though continuous spans produce more efficient structures that allow for shallower girders, the difference in depth of girders was only about 6 inches, and overall the additional cost due to construction and time outweighed the material savings costs. As you can see, our abnormal bridge geometry creates different span lengths. The shortest span is actually 86 feet, and the longest span is 141.5 feet. So in order to accommodate these different span lengths, we actually designed two different girders. A girder was designed for spans 120 feet and less, and another girder was designed for spans greater than 120 feet. In our alternative analysis, we also looked at the differences in steel versus concrete for superstructure material. We ultimately chose steel because of the lighter weight of the steel, as one of our construction sequences required placing a crane to lift the beams on the bridge. The heavier weight of the concrete and the heavier weight of the crane would cause us to over-design the structure a lot more than the steel. Here we designed the small steel girder design. It should also be noted that we did design this, or we looked into using rolled shapes for this instead of just plate girders. However, even the largest W44 cannot accommodate the L/500 deflections that are specified by the AASHTO Pedestrian Bridge Design Guide. The large steel girder design is 6 inches deeper, and this is accommodated in our piers, which Laura will talk about more later on. One thing to note is that we use 70 KSI steel for the bottom flange, or high performance steel, It said that it's more efficient to use high-performance steel in the bottom flange in positive moment regions. This also helps to lower the plastic neutral axis into the top flange from the stiff and relatively thick concrete slab, and therefore all of the concrete is in compression and most of the steel is in tension. The other thing that we would like to note is that bearing stiffeners were designed, although they are not pictured here. The bearing stiffeners help to accommodate for maintenance. The bearing stiffener or the bearings do not last the entire 100-year life of the bridge and therefore will need to be replaced. The bearing stiffeners allow those additional jacking forces to be accommodated when this needs to happen. Additionally, in our superstructure design, we included cross frames that will accommodate the lateral wind loads and provide structural stability. We use K-frame or K-brace type braces because the ratio of spacing to girder depth is greater than 1.5. And another thing to note is that since our bridge is skewed, there will be differential deflections between the girders. However, since our bridge is not skewed greater than 45 degrees, the differential deflection loads will not be greater than construction-induced forces. So now I will pass it off to Shar to talk about deck design.
Thank you, Becky. So for the deck design, we opted to use precast slabs over the more traditional cast-in-place concrete. We believe precast slabs are less time-consuming and more economical. They also have the added advantage of no formwork necessary. And when you're spanning a structure when you have a structure spanning I-579, formwork becomes a huge liability. So it's something that we did not want to use at all. We will also be using lightweight concrete, 5 KSI strength and 10-inch thickness. The lightweight concrete is being used to take some of the load off of the girder. The 5 KSI strength and the 10-inch thickness are being used to plan for future loads and hopefully help reduce maintenance in the future. And then we will be using a Zypex additive, which is basically just an additive in the mix design for waterproofing. And then lastly, we'll be using a 2-inch cast-in-place future wearing surface, which is just another protection layer for our load-bearing precast slabs. So for the deck design, the load cases that were considered were the dump truck with the dead load without trees and a 90 PSF live load for the pedestrians with the total dead load. So to analyze the dump truck going over the slab, we did a line beam analysis and the following moment envelope was created. As you can see, the blue line represents the positive moment and the orange line represents the negative moment. Please keep in mind that these values were calculated after the strip width equations were implemented. And we also want to do a little comparative analysis. So we created a finite element coarse mesh for our slab and then loaded our dump truck on it at a critical location just to see if my structural analysis on the moment envelope was correct. And the numbers did come out relatively the same, so we were pretty confident with the line beam analysis. And as you can see on the right, it's an exaggerated view of how the slab will deflect when the dump truck gets loaded onto it. So comparing the dump truck with the pedestrians, it's pretty clear to see that the dump truck will control the loading for the deck. It has a higher max positive moment, max negative moment, max overhang, and max shear. And then here's a summary of my results for the deck. Please keep in mind that the additional overhang reinforcement was only designed for vertical loads. And here's a cross-section drawing of the deck. That concrete parapet will just be used as a retaining wall to hold in the soil and nothing else. And this cross-section shows the transverse and longitudinal reinforcement used in the deck. And so here's our slab layout. And as you can see with the weird geometry we have, we're not going to have a one-size slab fits all. So we were able to bring it down to about 4 precast slabs that we designed and will order for construction. And I would say these 4 precast slabs cover about 99% of our structure. And so for the deck joints going perpendicular to the girders, we're going to use 1.25-inch diameter dowel bars going the length of the slab. They're going to be 15 inches long and spaced 15 inches from the exterior and 12 inches on the interior. And now here's a 3D rendering of the slab showing the dowel bar, and another 3D rendering showing the top rebar of the slab sitting on the girders. And now I'll pass it on to Carol to talk about shear stud connections and drainage.
Thank you, Shar. So in addition to the analysis that Shar just discussed, due to the complexities of the geometry of our structure, we also decided to run it in STAAD to confirm our values. And this is, the most conservative values were used for the analysis. But here is a wireframe model of our base structure. And here is a 3D rendering of the composite deck. On this slide, we have a cross-sectional view of the composite deck and the shear studs. There are 3 shear studs, size 3/4 of an inch and spaced 16 inches apart at each support. There is a 2-inch clear cut wearing surface of concrete poured on top of these connections. And in the middle, there, the support, there's going to be prefabricated pockets where the shear studs will go in, and they will be filled with grout on site. And then, as you can see on this image, there is a 1% slope on the deck, which will be used for our drainage analysis. For our drainage analysis, we use the rational method, Q equals CIA, as most of you are probably familiar with. The intensity we determined was 9 inches per hour. The runoff coefficient was 0.6, which is a conservative value, and the adjustment factor is 1.25. We designed for the 100-year storm because that was the most conservative duration, and the flow for the design is shown right there. Currently, any rainfall at this site is collected and drained along I-579. But after our structure is put in place, the rainfall will follow the pattern of the 1% slope and will accumulate in the lower left corner. At the abutment out of this point, we will have a pipe that will extend under the park and will reach the inlet, and it will tie in there at the inlet at the intersection of Bigelow and Chatham Street. Historically, we all know that Pittsburgh has issues with stormwater and wastewater sewage overflow, so our design is trying to combat this problem. Here are the dimensions for the pipes we will be using. The first one coming from the abutment is 6 inches in diameter, and the next one will be 24 inches in diameter to accommodate for any backflow. Finally, the third pipe that will be tied into the inlet at the intersection will be 18 inches because it is the required minimum. For material for the drainage layer, we decided on the 4-drain FD60. For those of you who don't know what this material it is a thermoformed recycled hard plastic, and it is very lightweight, and it has a high retention rate for water and a high drainage capacity. And now I will pass it on to Laura to discuss the bearing and pier design.
Thanks, Carol. So for the substructure, we considered multiple pier geometries. Our first alternative was single span. This would be ideal because there would be no interference on I-579. However, as Becky discussed earlier, this alternative was very expensive. Our next alternative was 2-span. So this involves placing one line of columns on the elevated I-579 southbound ramp. Considerations for this alternative include slight lane relocation and also consideration of how the piers will affect the existing retaining wall. The third alternative was to switch from 2 to 3-span. So for this alternative, you have one line of columns on the I-579 northbound ramp, and it then changes to 3-span. However, with this alternative, there were shoulder width requirements that were not met on the I-579 north ramp. So we decided to go with our 2-span alternative. So this shows the existing geometry of the roadway. There's a 12-foot shoulder. Adjacent to that is a lane that ranges from 12 to 20 feet, and adjacent to that is another 12-foot lane. With the addition of our 4.5-foot wide pier, the 12-foot shoulder will be maintained. The lane adjacent to that will be reduced to 12 feet, and the lane adjacent to our piers will be roughly 12 to 16 feet in width. We wanted to include any extra width in the lane adjacent to our pier to reduce crash ratings. So we considered multiple pier types for our design. We eliminated solid wall pier from the design. This would be too much concrete and too much interference on the existing roadway, so it would be too expensive. Preliminary designs were developed for the hammerhead pier and the rigid frame pier. For the hammerhead pier, overturning of the pier cap was a major concern. So we concluded that for hammerhead piers, they're more suitable for more narrow and taller structures, whereas the rigid frame pier is more suitable for a wider and shorter structure, which is characteristic of our bridge deck. The rigid frame pier reduced the amount of concrete required by 37%, and aesthetically is the better option as it matches the existing piers under the existing bridges. So we went ahead and selected the rigid frame pier design. This is a 3D schematic of our rigid frame pier. There are 17 columns spaced at 18 feet. We also considered other spacings of 12, 16, and 24 feet for the columns. The pier cap is separated into a north pier cap and south pier cap. This is because, as Becky discussed earlier, we are switching from larger girder shapes to smaller girder shapes. For the pier cap analysis, we used an approximate analysis method for simple frames, and from this we were able to calculate end cap shear and positive and negative bending moment. So these were our values in the north pier. Strength 1 and service 1 moments were analyzed, and that helped determine the design for the cap. In the south pier, these numbers were reduced slightly as there are shorter spans over top of this pier, so there is less loading at that location. For the column analysis, the vertical loads from the cap and superstructure were transferred into the column as an axial load, and then the shear and transfer loads were analyzed using Portal method, which yielded these values. These values were reduced. The axial load was reduced at the south pier. We also considered eccentric loading of the column, especially due to our construction sequence, and we considered longitudinal and transverse moments on the column. And our crash barrier, in compliance with AASHTO, was designed for a 400 kip impact load at any angle. So here's a drawing of our pier. We have a 4x4 foot cap, a 30-inch round column, and a 3-foot tall and 4.5 foot wide crash barrier. In the cap, we have number 11 bars to 9 at the top to resist negative moment, and 18 at the bottom to resist positive moment for the north cap. This was reduced to 15 bars in the south cap. We have 6 legs of number 7 stirrups at 7-inch spacing in the north cap, 7.5 inches in the south cap. In the column, we have number 11 vertical bars, 12 in the north cap, 8 in the south cap. Number 3 hoop bars spaced at 12 inches. And we have number 11 bars at 6 inches in the crash barrier, and also number 3 bars at 12-inch spacing. And this is a plan view of a section of the pier cap, and 6 bars from the column will extend 27.5 inches up into the cap. These are both 4 KSI cast in place concrete material. So the 27.5 inch extension up into the cap will form the connection for the cast in place structure. So here we're zoomed in on the bearings and pedestals. These will help transfer the load from the superstructure to the substructure. We have 3 combinations of bearings and pedestals. At the north, we have, these are designed for the large girders. These are designed for the large and small girders. And then these are designed for the small girders. So here's a summary of the dimensions for the pedestals, and also shown is a cross-section of our pier at a pedestal. As you can see, the reinforcement extends up into the pedestal. An important dimension to note is the difference in pedestal depth will account for our 6-inch difference in girder depth. For the bearing design, we use an elastomeric bearing with steel reinforcement. At the pier, we provided a fixed connection by designing 2 steel reinforcing layers in the bearing. At the abutments, we wanted to allow for thermal expansion, so we used zero reinforcing layers. And the bearing lengths are 4 inches less than the girder widths. This is to help transfer the loading from the superstructure into the substructure. Now I'll pass it off to Nick.
Thanks, Laura. Now we'll get into the subsurface design and the geotechnical engineering portion of our design. Luckily, with the rest of the Lower Hill District redevelopment project, there were many borings done in at reasonably close proximities to our structure. So we use borings close to our abutments and to our piers in order to design our foundations. Here's one example. It's just a boring terminated at 116 feet, and this gave us all the really general information that we needed to do our geotechnical and foundation designs. We had just general soil classification, blow counts, rock quality designation, and from these values we could get all the design parameters that we needed, such as cohesion, friction angle, and the ultimate strength of the rock that we were intending to reach. So one of the first parts of our foundation and geotechnical analysis was to make sure that the existing 2 retaining walls on either side of the roadway were capable of handling the additional overburden pressure from our new structure. That turned out to be 675 PSF. So we analyzed these existing walls using the existing designs that are pictured here. And you can see that we analyzed them for overturning, sliding, bearing, settlement. And we also considered the slight modification that we had to make to them. We're going to be saw cutting the top off just to accommodate for the different heights of abutments. So all that being said, the walls are fine and all the target safety factors were reached. So no major structural modifications will have to be made to the retaining walls. The abutments will be offset 4 feet from the edge of the existing retaining walls, and so an extra 10 feet of girder extension will extend from the edge of our structure. And these square shapes will designate where each of the bearings that Laura just talked about will be located. The abutment in total is 12 feet wide, 6 feet deep, and they'll extend along the entire edge of each side of our structure. The circles around these bearing points designate the micropile locations that we decided to drill at these points. These micropiles will be 70 feet deep. They'll be drilled through various shales, clays, and silts at the top, and then eventually reach a very solid, dense, and strong limestone at the bottom. That's where the end bearing will be resting. They'll be about 12 inches in diameter, half an inch thickness. The group efficiency, as you can see in this previous slide, they're spaced out significantly, so that won't be an issue with the settlement of the group efficiency of these piles. They were designed for the axial capacity, which incorporates both the end bearing and the side frictional resistance of these micropiles. And also we selected micropiles to resist any future additional loads and also potentially uplift or eccentricity due to construction or future load increases over time. Also we designed for lateral loads. Settlement, which you can see over on the right, was determined to be 0.45 inches per pile, which is well within the range, 2-inch maximum. And also the grout strength for these micropiles was examined in the design. So below each of the piers that Laura just mentioned, we were going to have drilled shaft caissons. These will be 40 feet deep to reach the bedrock below. They'll be a 30-inch diameter, just like the columns above. And they were designed in a similar way using Beta method for friction resistance and Meyerhoff's approximation for end bearing. for the axial capacity, just add those up, and that's your axial capacity of the pile, of the pier rather. We also examined eccentricity and lateral loads, in part due to the tributary area for each of these piers was much larger than was present on the micropiles. So that was a little larger, and you can see that shown on the right, but the safety factor was achieved. And also settlement for these was 0.23 inches, so that's well within the 2-inch maximum allowed as well. I just want to tie all this in and get our construction managers involved. Here's Nate Hyde.
Thank you, Nick. All right. So the first thing I'd like to touch on for the construction management portion is the scope of work. Nick already did a pretty fabulous job reviewing our description of work as well as our deliverables. So the next item is exclusions and constraints. We do have a few exclusions for this project. Our project includes only the design and construction of the spanning structure and site landscaping. Future buildings, traffic studies, and crosswalk improvements are not in our design scope. We also had a few constraints, which include traffic pattern disturbances, limited laydown area, and material and equipment availability. We made several assumptions during the project with the assistance of field professionals as well as professors. As far as major tasks goes, we came down to 5 milestones. They include site prep, substructure construction, erection of superstructure, addition of deck, and landscaping. These milestones I will cover more with the work breakdown structure. Our work breakdown structure we created very early in this project timeline using Excel. However, we eventually imported it to P6 so that we could utilize it to create our construction sequence as well as our final schedule. We utilized the tabular organizational method to create it and ended up with about 5 total levels. You can see the first 2 level summary in front of you. And at the end, at the 5th level, there were 113 total specific activities. This is a summary of the P6 work breakdown structure. You can see that the dark blue is level 2, gray is level 3, light blue is level 4, and obviously since there's 113 items for level 5, we couldn't show them here. Next, I'm going to pass it on to Graydon so you can talk about our cost estimate.
Thank you, Nate. In the process of going through this, we tried to develop bid items that would be associated with our project. As you can see, our total cost came out to $22.2 million, but after markup, our final bid total would be $23.8. Our total cost of the bridge superstructure was $16.9 million. That's excluding our general conditions, which were shared costs that were spread throughout the entire project. An example of one of those spread costs would be our risk contingency. Throughout the course of the project, we developed a risk contingency plan where we analyzed risks that were associated with our construction, determined the probability or estimated the probability that these risks would happen, and then tried to associate a monetary value with that, and then added that back in with our general conditions. As you can see, our cost for the bridge superstructure was roughly $360 a square foot, and the cost per pound for steel of installation, which includes the purchase, shipping, and manufacture of the built-up section on site, came out to $1.76 per pound. All of these costs were generated using RS Means, which is an accepted industry standard for costs, and as well as production rates with our estimate. As well, we consulted with professionals for better defined costs for some of the specialized construction on our job site. With the cost estimate, we did a little bit of value engineering in an attempt to build the highest quality project for the owner, as well as reduce the cost overall. This is just an example of one of the many cost comparisons we did throughout the course of the project. This was just 1 span versus 2 span, and as you can see, the steel girder cost is much higher than the 2 span cost. And 1 span does not have the rigid frame, so obviously that doesn't have the cost in that. And by the end, you can see that by using 2 span, we're saving roughly $3.2 million. That should be noted that those costs also include manpower and hours associated with building and constructing the different parts. For our construction schedule, we had a total calendar days of 515 days with a notice to proceed on January 16th, and completing the next year in on June 14th. This, we realize, is a very aggressive schedule and would be achieved through multiple crews working on simultaneous activities. We were limited because we have a lot of concrete on our job site, so we were trying to keep all of the concrete poured and finished within the weathering seasons permitted. Just to note, the superstructure was in with the wearing course poured and with the 28-day cure by November 29th. Below is just a sample from the schedule as well. With the estimate and schedule, we had to take into account some constructability considerations, and the first was selecting a crane that would work on our job site. With selecting the crane, you have to consider your largest radius, the heaviest pick that you could reach, as well as rigging and anything else associated with that. For our project, we had a longest span of 141.5 feet. So that becomes your longest pick plus the distance to the center of the crane radius and plus the hook and block. And with all that, we selected the Manitowoc 14,000 Series 2 with a 184-foot boom. It should be noted the crane is self-erecting, so we don't have to designate extra manpower or equipment just to build the crane and demobilize it or move it around the job site. Additional constructability considerations for the project were the existing pedestrian tunnel on the west side of the project, the roadway closures and detours that we have during the multiple phases of our construction, transporting the long beams, which it should be noted that the 110-foot beams are capable of reaching, or the 120-foot actually, are capable of reaching the job site, but the 140s are a bit of a difficulty, so the crane selection actually incorporates this in that the longest span is on I-579 South, and the crane can reach out onto I-579 and pick the beam up from the abutment and then set it off to the side or install it thereafter. Continuing with the considerations, we have lighting, ventilation, vibration monitoring of the two structures, the two existing structures on either side of the project for any movement during construction, as well as any traffic signal retiming that we would need. And with that, I'll hand it over to Nate to go into a little more detail on the pedestrian tunnel.
Thank you, Grady. During our site visit on September 13th, we recognized something which we were unable to visualize through Google Earth alone, and that is this pedestrian tunnel, which connects two portions of Crosstown Park. As you can see, it goes underneath Bigelow Boulevard. So we came up with 4 different options to address this. We could either build stairs and a retaining wall. We could also add a pedestrian bridge, which will span over the existing concrete ramp. We could also extend the tunnel, or we could close the tunnel. Options 1 and 3 require ADA considerations, and options 1 through 3 require very considerable increase in costs and time for the design and construction management portions. So ultimately, as a team, we decided to move forward with option 4. Another thing Graydon mentions that we had to take into consideration were roadway closures. Because of that, we came up with 5 different phases during the project that we would have to shut down different portions of the road. The first phase occurs during installation of the piers. It calls for the closure of Ramp D and as well as an I-579 southbound 2-lane shift. Phase 2 occurs during the demolition of the west retaining wall parapet. Phase 3 occurs during the demolition of the east retaining wall parapet. Phase 4 occurs during the installation of the eastern half of the beams and deck slabs. And Phase 5 finally occurs during the installation of the western half of the beams and deck slabs. This is our detour plan for Ramp D. We do have detour plans for every lane on I-579, but for the sake of time, we decided only to show you Ramp D. For this detour, traffic will exit Crosstown Boulevard onto Forbes Avenue. It will take a right onto Grant Street and proceed directly towards 7th Street. So for this project, we obviously did complete a full schedule because obviously that was necessary, but because we believe our project is a little bit more complex, we wanted to give everybody a visual experience to hopefully be able to comprehend it a little bit better. So due to that, we created an animation on 3ds Max. So looking at the site right now, you are basically hovering above PPG Paints Arena, looking west. All right, so we're going to rotate around the scene here. You can see the different elevations of the I-579 ramps. We're going to zoom in here, and you'll see the foundations start to appear for the pier. After this occurs, the pier columns and cap will fall into place. Following that, we're going to take a look at the park section. This area will demo the sidewalk, clear and grub, and strip the topsoil. We'll also seal up the pedestrian tunnel. Then we'll excavate the west abutment side, saw cut the top portion of the retaining wall, drive micropiles. After they are load tested, we will form, pour, and cure the west side abutment cap. We'll perform the same thing on the east side as well, starting with the milling of a portion of the asphalt. Then we'll drive some micropiles. After load testing, we'll form, pour, and cure the abutment cap. Then the east side girders will be put in place. Following that, the east side precast deck slabs will be put in place. And after the east side is basically finished, we can start placing the west side girders. Once the west side girders are put in place, we can start installing the west side deck slabs. After this is complete, we can pour a concrete wearing course, which will make our deck composite. That'll be followed by a root barrier, which will be followed by a protection layer, which will be followed by a drainage layer. Finally, a filter sheet will be put on top of it. Then we will mill the rest of the asphalt parking lot. And then we will go on to form, pour, and cure parapets as well as stairs to help keep all of the soil that we're going to import on the site, which you'll see shortly. After that, we'll pour the sidewalk, put in the grass sod, and finally install the foliage and other landscape.
He spent so many hours making that, so he definitely deserves the round of applause. With that, we'd just like to acknowledge everyone that helped us throughout this project, especially Dr. John Euler and Professor John Sebastian, who helped us the whole way through, especially all the other organizations that helped us along the way, in particular the Sports and Exhibition Authority. There's too many people to name right now, but thank you so much to everyone here and everyone who helped us on this project. At this time, we'll take any questions that you might have.
I'm a little confused. The fact that at the very beginning, when you showed the project,
Yes.
you showed a Quebec and some running water fabric going through concrete. But even if I remember, you mentioned you had 6-inch concrete with 3-inch ribs and so forth. What happened with that? Was that just illustration?
No, that's actually basically the standard loading that we use.
Well, it's not loading. That is not a loading. That is a standard 6-inch deck construction. And then later on, you have come up with the idea of precast concrete slabs, right?
Mm-hmm. Yeah.
And that's fine. Did you use any composite action in your design?
Yeah, we did analyze both the girders and the deck as a composite material, and we used the shear studs as well as the wearing surface
Yeah,
on
but
top of that.
If you look at your sketch, you see where your shear studs are?
Yeah, let me go back to that real quick.
Yeah.
Mhm.
Yeah. You are using, are you gonna fill that with what, somebody has to explain that, how are you gonna put that? You see that your slab sits there?
Right.
I think if I'm not mistaken, your thumb flange is 18 inches,
I think so, yep.
something like that. 1.5 inch thick, 18 inches wide. And then your studs, I don't know the spacing, maybe 3 inches or so.
That's about right, yeah.
And then, are you gonna fill that with what?
That'll be filled in with the concrete wearing surface. So it's going to be 2 inches over the entire deck, and then whatever space is in between there will be
And then
filled with the
that-
concrete.
those studs are going to completely interact with the slab?
Yeah, that's correct. Hmm?
Who said that?
We might have missed that, or we should have talked about that in the slide with the slab design.
I did discuss this with one of our structural engineering professors, Dr. Harries, who says,
I have doubts about this composite action.
Okay, we'll have to look into that and consider your suggestions.
I mean, the continuity of the concrete is not there.
Okay.
And,
Are you concerned with the wearing surface sort of
no, it has nothing to do
attraction?
with that. It has a structural function.
Okay.
You know, they are called shear studs.
Mhm.
And what kind of shear they are transferring, where they are transferring from, I have a little bit answer.
Okay.
So I need some explanation. Otherwise, if you told me that there is no composite action, it would be fine.
Okay.
But you cannot assume one thing and do the other thing. Your
Right.
assumption and your design and your construction should be, complementary.
Mhm. Yeah. Sure.
Yeah, I just want to say, you guys did a great job. You thought about lots of different elements. I appreciated the way you kind of walked through the construction sequence. My favorite was when the excavation just blew dirt up into the sky.
It's really that easy, so.
Gravity's free.
I was a little curious. One of your assumptions was that you're going to have to place a crane on the new structure as you build it. Was that the second placement? Did you look at other ways of doing it? It seemed like a key assumption. What was keeping you from building it, your two-span structure from the perimeter?
So that's actually what we did decide to use the perimeter. Initially, we considered, do we put the crane on it or do we not? So we considered both of those. But in the end, the dump truck actually controlled the loading more than the crane anyway. So we just included that in the presentation just to show that we did consider that.
Okay.
But in the end, that didn't dictate our design and it didn't affect our construction schedule either. So that sort of was ruled out. It's simpler to build it from the abutments.
Okay.
That's what we decided.
May I follow up with one thing?
Yep.
Because the picture is right there. You say interior shear studs located at the middle support.
Right.
You bring with the crane and lower the slab.
Mm-hmm.
Where are the studs?
They won't be installed yet, and there's a prefabbed out section. Yeah, a pocket, and those middle supports. And then after it's
So
lowered
the
in.
Studs are on the steel beam flange,
Yep.
and then you are going to have your slab sitting on that?
Well, it's the reverse. The slab is put on first, then the studs are installed, and then those prefabbed out sections are where the worker would install those studs every 16 inches along that girder. And that's only for the middle support, because you can't see it in this cross-section drawing.
So when you bring your slab, there is no beam
What do you mean?
there. That girder.
All the girders are installed first, and then that slab is placed on top.
The girder is installed and you have the studs on.
Not yet.
No, the studs go in afterwards.
Yeah.
You can install them after the fact that the deck slabs are put on.
So,
They're prefabbed out.
Pockets.
They're prefabricated out, like prefabricated pockets.
Yeah, typically there's reinforcement that runs across that pocket that engages the concrete that you place in there, and the studs are shot after the panels are installed.
Correct.
Right. Right, exactly.
Back here.
When you evaluated the pedestrian tunnel and decided to close it, was there any consideration given to the public art inside and the cost to remove and preserve that?
We didn't actually look at the cost. I don't think that's a great question. We did when we visited the site. We saw that, and we were hoping that maybe they could remove that or do something with that. We should look at the cost, but we did consider all other alternatives, including like the pedestrian traffic. It'd be rerouted above. We would retime the signals, but yeah, considering the art's a good point too.
Yes, huge topic of discussion these days.
Thank you. Go ahead.
Keeping along with that tunnel concept, did you realize that maybe you are building a tunnel on 579?
Yes.
Did you take that into consideration, and what complications that may create for the traffic down below?
So based on AASHTO standards and verified by PennDOT, this is technically considered an underpass, just a very long underpass. But we've also considered fire safety, ventilation, and the lighting that will be needed under this, just because it's going to be dark in there when it's such a large underpass.
Those things are
That's included in there too, yeah.
Ventilation.
Yep.
And then with regard to the art up above, I mean, this is going to be a showpiece for Pittsburgh.
Right. Yeah.
I would imagine there's a lot of aesthetics, you know, benches, fencing, lighting, things like that, irrigation.
Mhm.
Is that all considered?
Yeah. Yeah, that was all added in the landscaping for the project.
Go ahead.
I have one more. Did you consider, did the weight of any stormwater that you will hold, did that affect any of your calculations? Because especially if this is getting public money, you'll be required to hold or reuse a portion of that stormwater on site.
Right.
So was that,
Yeah, so we considered both the loading of the saturated soil in our structural design, and then also with that that drainage outlet, we sized that so it would basically act as a retention basin, so that it would flow into the combined sewer system at the required rate. And then we had thought about, we didn't do any complete designs, but potentially you have a pump down there, maybe you pump it back up and then water it on a dry day or something like that. So that's something we could consider.
Good work.